What is a type? Why do we use types? Forget Newtypes for now, why do we use types at all? If I show you this binary value, can you tell me what it is? We can rule out a few things. It's 64 bits, which means it's definitely not a boolean or a character. It's also too long for an IPv4 address and too short for an IPv6 address. More likely, it's a number, either an integer or a float. Let's try parsing the data as a few things. Here's the data, and for reference, this is it as bytes. So, it could be a huge integer. However, it's probably not a float. Well, this looks right. So it's probably a short UTF-8 encoded string advertising our new collection of videos. But who's to say really? Without knowing for sure, we're just guessing. Types turn data into information. Without knowing whether we're looking at a number or a sequence of ASCII characters, we'd have a really hard time writing code, and more importantly, what we write would be very error-prone. Without type information, there's nothing stopping us from accidentally passing a boolean to a function that expects a complex user structure. We start having to depend constantly on runtime checks to make sure any data our functions receive is valid before trying to process it. All modern languages, even ones we may not usually think of as being typed, come with their own built-in types that usually cover, at the very least, floats, strings, lists, and objects, or dictionaries. This helps us reason about the data stored in memory. You'll notice I didn't include integers in the bare minimum types. This is because some languages opt to store all numbers as double precision floating points. This only really becomes an accuracy issue for integers over 2 to the power of 53 though, which is over 9 million billion, so I think we can give them a break. But is it enough to consider hello@example.com to be a string? It technically is a string, sure, and we could manipulate it as one. But in the context of our software, it might be that there is a meaningful difference between hello@example.com and helloexample.com, in the same way that there's a meaningful difference between space for the win and 6,292,731,980,616,396,915. Why aren't normal types enough? Here's some code that represents years, months, and days. For simplicity, I've used U64s for everything. Yeah, we should probably use U8s for the month and day, but the size is relevant to the point. Not every language has different sized integers, or, as we discussed, integers at all, and U64s are going to help me demonstrate a point at the end of the video. However, we can immediately identify some problems with this. First, there's nothing stopping us from using valid U64s to represent invalid data. I can make all of these numbers invalid by changing them to 0. Second, there's nothing stopping us passing any valid number to a function that's supposed to take a month. In this example, we've got a function that takes a month and returns the name of the month in English. However, because you might pass in a U64 that's not a valid month, that means we need to validate the parameter and return a result. I'm using a unit struct for an error here. Ideally, we'd go through the steps to impl error properly, but I hope you'll forgive me if I skip that for this example. Our function checks that the number given to it is between 1 and 12. Unfortunately, it doesn't stop us passing data to the function that isn't supposed to be a month. Ross is happy to let us pass in data that's supposed to represent a year or day, and that's a mistake that may be missed even at runtime. What I'd like you to take away from this is that the concepts of days, months, and years are meaningfully different within the domain of our application here. There is contextual information that we're ignoring about the data. We need to know more about the type of data that we're dealing with beyond it just being a number. This is what the Newtype pattern is for. Introducing the Newtype. To oversimplify a touch, Newtypes are wrappers around existing types that provide the context for the information stored within. First, let's prevent days being passed into functions that should only take months. Here, I've wrapped our U64s in tuple structs, one for each of year, month, and day. I've also modified our function to explicitly take the month type. This is immediately more informative to anyone reading your code. Even better, if we try to pass a year or day into the function, we get a compile time error that very clearly tells us what's wrong. Our second issue is that we can still produce invalid values such as month 13. We can fix this by controlling access to the inner data. For example, we could restrict the instantiation of our types to a constructor that validates the input. Let's focus on month. We need to make sure that the interior of the struct can only be instantiated or edited by things we control. In this code, I've moved the month Newtype into a month module. This lets us protect the internal data so only things inside the module can see or change it. And we can control exposure through marking things explicitly as public. So the interior of our unit struct is not public, but our constructor is. Now we can validate the month when it's constructed, returning the error if necessary. Since we can no longer instantiate an invalid month, we can fairly confidently remove the result from any functions like getEnglishMonthName. We still technically have to deal with every possible U64 in the match statement, but theoretically, it has to be between 1 and 12, and if it's not, something has gone horribly wrong, so I think a panic is now in order. I'd say there's still one improvement we can make here, at least for months. Our program is written in English, so why use numbers to represent the months in our code at all? Plus, dealing with numbers are why we still need to have that panic in our getEnglishMonthName function. We can change how we model month in our code without changing its underlying numeric representation by changing it to an enum and specifying the enum's discriminant type with the repr attribute. Depending on your data, you obviously may not need to specify this, and again, a U8 would be more appropriate here, but I still need to make that point later. Anyway, by using an enum, we can remove the code branch that was theoretically impossible anyway, and I'd say this is a lot easier for anyone reading the code to understand. So that big point I've been working up to. These types only exist at compile time. In memory, in our running program, these types are all exactly the same. In this program, we've constructed each of the month types we've discussed. I've had to give them different names here, but don't worry, they're otherwise identical. We've got our U64, our tuple struct, and our enum versions. Each version looks very different, but conceptually represents the same information. I found this function that can extract the memory of any given value regardless of type. Passing each version of our month in for September gives us back a byte array. Exactly the same byte array, in fact. This is why I stuck with U64s for what it's worth. Types aren't real. They provide us, the software engineers, information we need to structure our programs better, and we can use the type system to prevent us from making mistakes. But at runtime, it all disappears. Trade-offs. There seems to be a lot of extra work going on here. We need to add more validation, extra error types, and all the extra work they're supposed to involve that we skipped here, not to mention how verbose the match statements were for the enum version of our month Newtype. That's true, but we've been focused on the Newtype, not the impact it has across our program. By moving our validation code into a single domain type, we've decluttered the rest of our program. Let's think about a more complex type like an email. Using built-in types, we just create a validator and call it done. This code is straightforward, terse, and requires little testing. However, every time we want to use a string as an email, we will need to run the validator. This not only could risk the same email needing to be validated multiple times, but adds some significant risk, particularly as our code evolves. Anytime we don't use the validator for a function that accepts an email string, because we perhaps initially created it only in a context where the string has already been validated, we risk that function being reused with no validation somewhere else. Worse, it's easy to imagine that our software might end up with multiple validation functions, each following slightly different rules. In this example, we're using my good enough no false negatives approach, but another engineer might write a different validator. Perhaps they come up with a regex, which catches more bad emails but has a small chance of flagging a false negative. Then we have two models of what an email should be inside our software, and they no longer agree with each other. Here's what it might look like to make an email Newtype. We've added an error type for potentially invalid addresses, and this time I did those extra steps to implement the error trait. Next, we've got our constructor, which calls to our validator, though the validator logic is identical. We've got one test for our constructor and one for our validator, though that one's the same as earlier. Now though, we only ever need to validate the email when we create the data type, which will usually be when we're getting that data from an external source, for example, from a user or from a database. This will also mean we only have to look in one place if we need to change our email logic or fix any bugs. In conclusion, for a small amount of extra work, Newtypes give us centralized validation and error handling, reduced complexity, more information to understand the domain we're working in, and more defensive, safer to use code. If you enjoyed this video, don't forget to like and subscribe. Next time, we're going to look at another way the type system can be leveraged to make more rigorous code with the type state pattern. If that sounds familiar, it might be because we covered it in the Iris series. Hopefully, I'll see you then.